Hey gang, welcome to another Toolbox, Stunt Rigging Toolbox talk. You guys all like the machines, and I'm a machine rigger. I love the repeatability and doing stuff. That's why we have our Descender, our Ram, and I'm going to talk about one of the most underused pieces of equipment. Old days, they had them a lot, but because they were built so absolutely shit, they were do or die. They were really horrible geometry-wise, and you used to get your ass kicked by them. The common thing was you had to dial them up to 1,000,000 to get them to move. And then once they hit the actual geometric correct point, you got your knees stuffed into your ears. And it was very difficult to ride them. They were a real bitch because nobody really paid attention to the geometry. This is full stroke on mine, which is 46.5 degrees. It uses 2 cylinders. And it goes from level to 46 degrees. I can get more out of it. I have the stroke limited inside with springs, so it returns nicely. The point of these is you have to have the geometry correct first. I'll go to the whiteboard in a little bit, but this one is 300 millimeters tall, which is a foot for most of you imperial types, at the high point, okay? And when it's on the ground, that's the highest point, and then the platform, which you'll see down here, has springs, which are adjustable to give it some feel, so you have bounce to it. So when you get on it, it's just not a dead object. You can actually springboard it. You can get on it. As you push down, it's triggering and bringing you up. And there's always going to be, these valves are 40 milliseconds. So they're really fast, but still in the overall world of reactions, when you are playing with these and you hit it, you'll hit the trigger, and as your weight sinks down, it will come up and push you. So you have some feel to it, and it's adjustable. These were horribly designed back in the day. Everybody tried to make them as flat as possible. And I'll get into that in the whiteboard just as a quick discussion. The reason we're doing this today is because I have to go through and check the cylinders. I have my leak down tester on the device, something I scabbed from racing technology, which I used on all my fuel bikes and everything. So you put air into it and you set it at a set point, and it has 2 gauges, and it'll tell you what's in the system versus what you're putting in to see what the discrepancy is. Normally used to see cylinder head, ring seals, and stuff like that. But it works with cylinders, and this is something I check with all the Rams. This is what I check with anything that uses pneumatic cylinders. These particularly use 100 millimeter or 4-inch cylinders. Now, part of the whole problem with getting it so flat is that in the geometry of pneumatic cylinders, which funny enough, there is a book. I mean, face it guys, this is industrial tech. This ain't space shuttle. This shit's been around for 100 years. They use this to move everything around aircraft plants, auto plants, food plants, air, giant fucking, vane compressor outside puts air throughout the entire plant, and all these cylinders are used with a variety of banner infrared eyes and things to automate processes. They have to be exact. They have to do the same thing every time. They need to move X, Y, Z coordinates. That's how it works. So they're very capable of all of that. What we've done, and on this one, it's different than the Rams. The Rams we use backwards. We pull with them, which means we put it in on the rod side, and that's bullshit. It reduces your overall force, and it's not really the correct way. That's why so many guys' Rams work shit, because there's too much friction, the pistons aren't the right way in the bore, etc., etc. And with any cylinder technology, you can only put as much air in as air you can get out on the other side. It's a closed system. So these, like all my others, have huge amounts of exhaust on them, so that as they go up, there's no resistance, meaning we can use less pressure, which makes it much safer for the performer. You aren't using, like, there's some guys in England that make these, and they're like using tiny ports in 600 PSI, and it makes no sense, and the geometry's wrong. So basically you end up with something that's really dangerous to be on. The point of this is to create the look you want and be safe, okay? Here's what you get. And that's why these got seriously maligned in the last years. And people don't use them as much, but they're extremely viable. A small trigger box, a small pressure bottle, and boom. This at 10 bar will take a 100 kilo person and send them 10 meters, 30 feet. in a nice parabola. Now look up parabola, and there's formulas on it. That's why I only come this high. There's ideal numbers for parabolas. There's formulas that teach you, and you can actually see what the arc is going to be from your takeoff angle and your takeoff height and your takeoff speed and your force, and it will calculate the distance you travel in an arc and what that arc is going to look like. Too short of an angle, you pop straight up. Too long of an angle, you auger straight forward. I've compromised. These travel about 45, 46, this one. You probably aren't on it until the end. You're usually on it about 37 degrees, which is our optimal trajectory. It makes for a beautiful arcing trajectory. All of these factors play into how these are built. Now, part of this whole device is in getting the geometry right. So, cylinders work when they push. We're pushing on the face, so it has to push something forward. This is a giant lever. The pivot is in front. So you are taking a reverse mousetrap. You are pushing this lever this way. Now when the lever is flat, the cylinder is pushing flat directly at the pivot. So in some way you need to rearrange the geometry so that you are pushing against a lever arm that will function. And cylinders in that aspect, in the book that tells you how to design this stuff, they will work from 45 degrees to 135 degrees, okay? So basically what we've done, so it's a 45 degrees of travel, okay? From here to here, like this, okay? Okay, so they go from here to here. Boom, 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 boom. Or it's 90 degrees of travel, excuse me. The math in the morning. So that 90 degrees is this, but you can arrange it in any way you want. But a cylinder will only push here and end here. Okay, so your 90 is a V, okay? The problem is, if you flatten this to here, okay, and you're pushing straight this way, the lower you come and the straighter you push, the more you push at the pivot. Okay, so you have to create leverage. The geometry makes or breaks these things, okay? So I've arranged this when it's in its down position. The front is sloped back 10 degrees. It's pushing against the pivot, and the cylinders, because of their diameter, can only get so close to the ground. So they sit at about a 35 degree angle. So the combined angle is 45 degrees of where they're pushing, hence the 300 millimeter height. Now, if these were not 4-inch, if these were 2-inch, I could probably make this lower in front with the same geometry. The issue then is, with a 2-inch cylinder, I'm having to use much more pressure to achieve the same result. So I standardize everything on a 4-inch or 100 millimeter ram. Parts are interchangeable. I have all the bushings and seals and etc. in stock. So I standardize, which means they can only, because of their size, the pivot here, the actual center of the ram, no matter what you do, is 2.5 inches off the ground, or about 65 millimeter, 70 millimeter off the ground. 68 millimeter, whatever, you can do the math. So it won't come all the way down. So you have to arrange it so that your geometry is all correct, which is the whole point in when you design the frames. Most guys just, I want it flat, I want it here, and they put a pivot and put a cylinder on it, and they wonder why you hit the button and it takes 1,000,000 PSI because you're pushing directly at the pivot until it reaches a point where it comes up to a usable leverage point, and then it'll go. And that leverage point is going to depend on how heavy this whole thing is and what angles you're at. Now, there is actually a formula, funny enough, if you do the research, that tells you how much force you're exerting at the pivot versus exerting to do the work. Okay, so if you do this correctly, based on the correct formula, you can put 100% of your force into moving the lever arm and 0% of your force into pushing directly at the pivot, which is the most efficient use of this cylinder, which means you're going to be lower pressure and it's going to start pushing immediately from the bottom. It's not going to have a dead spot until it reaches a geometric good point. You're not going to have to overpressure it and then get hammered by the thing because now it's geometrically correct and it only needs 20% of what you've given it, but you needed all of that to get it to even fucking move at the beginning, okay? So this is the inherent problem with these things, is poor design. Again, guys who don't go to the resources, they don't do the math, they don't do the research. And I mean, this shit's ancient. It's been around. So this is the sample. This is mine at full stroke. I can disconnect it and bring it back down to the bottom and you can see it when I take the air off and let it down. I've got it on a stopper right now so it'll stay because I'm working on it. I don't like to get hit by it. But there it is at the bottom. Okay? So that at the bottom, the highest point is just back of the pivot. It's 300 millimeter. Okay? So when you stand up, that's the distance from the ground to about the bottom of your calf muscle. Okay, so hiding this is not really an issue. Back in the day, oh, it has to be hidden, it has to be. Guys, if you can hide a car pipe ramp, or if you can put, it's way superior and it's less than the height of your calf, bottom of your calf. And it's super efficient. They're really fun to ride. They're really great for gymnasts to play with. And if they're designed correctly, like this one, you have the math so that there's no weird point. There's no, it struggles and then kills you. This is a steady, perfect flight every time. Utterly repeatable, super easy to ride for novices as well as experienced people. And you'll notice, as I said, the front is kicked back. Let me see the actual measurement here. Yeah, I'm only 9 degrees back here. And the cylinder, if I put on it, is 30, so we're at about 40 degrees, okay? But because of the clevises and the arrangement inside, it's the minute it starts pushing, it moves this vertical lever, because they're at the top of this vertical lever. The distance from one pivot to the other is 250 millimeter. So you have 250 millimeter of lever arm oriented this way, and it's pushing here. So this goes from here to here, which is exactly what the book says. And there's no pushing at the pivot because you haven't tried to bring your mounting point down so low. Okay, the more you do that, the more you push directly at the pivot. So that's our initial thing. So a few other things we've done is it's a lattice chromoly frame, super light. And it's double fed, double cylinders, which means we can use much less air. I try to keep everything standardized. It uses the same trigger boxes as all the ratchets. We have an actual pressure pad instead of a micro switch. I hate micro switches. They get beat when you use this equipment. A lot of guys have this thing set so that you touch it, it pushes down. They may have springs or other rebound device under it. And then it clicks a micro switch and then it triggers the ram. All fine and dandy, except micro switches get hammered. I've used them on my fuel bikes, I've used them on everything, and then you carry 20 extra of them because they're not the most reliable things in the world. And if you hit them hard enough, meaning you bounce up and down and you trigger it farther, you either bend the sensor or you break the switch or. And here you just use molded rubber trigger pads. They're an industry thing, you know, that's what opens sliding doors. It's what opens many things. You step on it and it triggers something. I have 8 or 10 of them in the trailer I use when there's complaints about not pushing the button at the right time from certain performers. It's really easy. I just string one out, put it down and go, just the minute you step there, you're gone. So it's on you. And there's no arguments. Even though I know my timing from drag racing over the years is, I know exactly what it is. So I'm very efficient on the button. But if there's any debate, it's like, here, do it, knock yourself out. If you're late or you're early and you haven't reached your mark, that's your mark. It's on you. But we use one of those because they're utterly reliable, repeatable. They take X amount of pressure and you can get them in various pressures so that when your body weight lands on it, you have to actually land on it to trigger it, not just brush it or touch it. It's not hair trigger. So it'll take, 15 kilos of force on it before it triggers, which is more than enough to be firmly planted onto the pad. It's not like your toe touches it and it goes and then you rake your shins or smack your knees or anything. This means you have to land on it to do it. And we use those. So those are all the things we've done to make this efficient. And like I said, it's all about geometry. If you don't have, this is part of the problem with people and equipment. A lot of people are allergic to equipment and they think it's shit. They do hand pulls all the time. That's great, but they're not repeatable. They're not the same every time. And I don't care who you talk to or who you think you aren't going to jump off a ladder at the same point every time. Here you're automated. It's the same no matter what. It's all on the performer of how they react, and they can fine tune their performance. But you have to make the machines correctly. You can't expect a poor machine design to do the job you're asking it to do. So there's a lot of details involved in these things. And the problem I have is that most guys don't do the homework. This is all readily available industrial, mechanical technology. And you can learn about it, or you can research it, or you can study it, and it will tell you just how these machines need to be built. And we just repurpose them. I mean, that's all we do with them, is repurpose them. So I'm gonna cut this off quickly here. I've got my button and I took it out of my hand because I just shot this the other day and I keep hitting the button while I'm talking because I'm fidgety. I'm gonna go to the whiteboard and show you just quickly what it is. And one of the most underrated, that's all we are today, is air rams. One of the most underrated, useful pieces of equipment. Explosion reactions, running flying shots. With rams, you always have a line attached. So it runs into various issues. You have to be at your correct pulley point. You have to always be correct with everything. And it becomes difficult. If someone's running at you, you can take up slack. If someone's running away from you, you have to give out slack on the running lines. And that becomes problematic because we don't have, I've designed a couple, I've just never built them. They're not cost effective to make, but you can make triggered clutches so that they can run and the line rolls out. And the minute you hit the button, it will lock the clutch, and then that's the ram and the clutch locked together, so then you can ratchet. And that's when people are like running away from you. And if you do it by hand, it's bullshit because somebody's gonna mess their mark. You're either gonna go early and the guy's gonna go boing on the end of the string and then trigger, or the guy's gonna have some slack because you've slammed the clutch closed, and you're gonna hammer the ram and he's gonna get whacked into slack, which is unpleasant. Problematic with rams. Whereas with these, you put it out there, the guy paces off his approach, it's there ready to go, you step on it, and all you do is react and fly. And this is particularly strong. Like I said, 10 bar for 100 kilo and you're 30 feet. And you can adjust this, of course, for height. In terms of how you take off on it. A shallow takeoff, you'll go more vertically. A deeper takeoff, you will go more linearly. And it's all based on, funny again, the math of a trajectory formula. All right? So that's just an overview today, quickly, of a piece of very underrated equipment that most people forget about. And that's because everybody's got horror stories of getting spit straight up in the air when they finally kick in and landing right back on the machine, or having their knees shoved up to their ears, or being too stiff-legged, and when it kicks in, they get their fucking knee joints hammered. All of those factors are just basic, simple geometry fuck-ups. If you don't build them right, you can't ride them right. So this is a sample of one that's done right. It's on an aluminum plate. You just walk in, anchor it down if you have to. And you just put a small trigger box and an accumulator next to it, and off you go. I have put high pressure regulators on these so that they constantly refill the accumulator. The additional problem there is for multiple use. So it hits, it cycles, it's ready to go, it hits, it cycles. The problem with those is they're not perfectly accurate until you start getting to very, very expensive regulators. And then they take X period of time to refill the accumulator back to pressure. So a high flow, high accuracy regulator is thousands, okay? They work great. I had one that was pretty good, but for the use of them, it's not like 20 guys need to go in a row off of this and you have 5 seconds to wait in between each one before the regulator sets up the accumulator correctly. So it's a one-shot deal. You know, you can put multiple of these around and use them, or use these in combination. You know, you can use one of these with somebody on a line with a take-up. You can flip them in the air and then ratchet them sideways somewhere else, like they got hit by some magical beast in the air. There's options. You know, you can use combinations of machines. You can use the descender and a ratchet. You can use the ram and a ratchet. You can use the ratchet and then a descender to end out. You know, these are all options. And with these machines, as long as you've made them correctly, they are utterly repeatable and you know exactly what you get. So that's just a quick one on air rams. I love them to death. They're fun. Even for an old man like me, they are fun because this is so safe. It's just entertaining. It makes you feel like you know gymnastics or something, even though I'm a fucking ton of bricks in the air. It's good fun and they work really, really well. All right, that's just a quick overview on an air ram. You know, pretty simple design. It's a lever powered by cylinders, and you get the geometry correct on the lever arm, and you have a very, very smooth, easy to use device. Okay, great. I'll hit the whiteboard now for just 2 minutes, and then we're out of this one, and I'll talk to you on the next one. Throw another little video in since we're doing this. Here it is with blocks under it. The airlines come in, and then I'll show you the underside as we take it out. I use quick pins on everything. You'll see that there's the upper clevises, the polished aluminum on the front lever arms. And you'll see that it's a lattice to the lever arm. And then you'll also see the quick pins and shafts down here where I've stashed them. And there's the back clevis mounts. To get the cylinders out, it's 2 pins and just push 2 shafts out on each cylinder so that it's easy to maintain, easy to service. It's utter simplicity. Form follows function. Keep it simple, folks. And that's what I always say about everything rigging-wise, everything machine-wise. If you can't see it and understand it, then you have done something wrong. So we've got it blocked up so it doesn't collapse on me. And then you can see here, I have springs, 3 on each side. There's an array. They're basically like valve springs, and you'll see a whole bunch of little holes. You can orient these springs forward or backward. The more forward you come, the higher the bounce. The more back you come, the less height it has. But they're a fixed weight. For if you're less weight, you use less springs. If you want more spring when you step on it, more rebound, more feel, you move them up into your pattern. So you can tailor this feel to how it is when this platform here comes down on here, you have a stepping feeling. And you'll see it's a very simple machine, a gusseted, triangulated frame of chromoly with a heavy pivot in front on bearings. And this is the electrical connections covered when not in use. And your trigger then goes from there with a mil-spec connector back to your rubber pressure pad here. And this is your device. So this is us, and these are the cylinders we've pulled out today. They're a little dirty and dusty, so I'm gonna go through them, taking the exhaust port filters off of them, and pulled the industrial clevises off of them. And we're going to now look at them, check them. We're gonna open them up by undoing, these are called tie rod cylinders, undoing the nuts on the tie rods, and we're going to pull the piston out and have a look at the bores, and then put them all back together and reinstall them in the machine. So that's how we do things. And notice everything's oriented right, left. As it gets taken apart, it will stay separate, cleaned, and put back together. Then all of that will get put back in here with the shafts. Just push fit, 4 shafts, 4 pins, it's done. Okay? That's how we like to make equipment. And if you look at how everything's done, it's all gusseted, cross-braced, triangulated. This is how you do it. And there's your lever arm with your large clevises. And of course, since it's my machine, I polish the clevises and stuff. Same with all of the body work. It's all been polished and then rhino coated with bed liner It's for traction. And you'll see here is our leak down tester. Sorry for the nauseating video, but that is a leak down tester that goes on the machine, and I dial in how much pressure in one gauge, and it tells me what the cylinders are holding in the other, and that is how I can check when it's all together, if I need to take it apart or not. In this case, I'm doing it because I want to. It's not that there was any leakage. And these large bolts here are what holds the clevis to the front panels inside the large front lever arms. And then all the little stainless screws are holding the hand-pounded cover on it so that you can't get your hands in it at any point. And everything you'll notice is triangulated truss for strength, because 100 kilos, 60 centimeters out from the edge, you're putting quite a load on the end of this, and you don't want it flexing and bending. All right? So that's just a good example of how things are built. Hey guys, as long as we're here today maintaining these, I'm going to talk about tie rod cylinders as well really quickly on the air ram. First things you always check is you check your rods for scratches or any problems. You don't throw the rag on the floor. You check your bushings for play or slop, okay? These bushings come off the front of the cylinder end plates. They're billet. You look at the overall, I've cleaned and wiped them down. Then tie rod cylinders actually have two end caps that are held by a connecting rod, tie rod, okay? There's a torque value on these, depending on manufacturer and what they are. But torque values are a little weird to use, especially because it's basically a piece of all thread. It's a long piece of steel. It's got threads at both ends. So you could screw it on, and if you're working both ends, what will happen is one end will always thread on more than the other. So when I do these, just as a little trick to get to the insides, I lock the rod and undo the nut. But prior, I use my calipers and I measure how much stick out is on every nut so that I can replicate it and coordinate it with the tie rod stretch value. Because the point is you're putting these caps on, and this metal actually stretches to hold the end caps sealed. Now these are good to 64 bar, okay, so 1,000 PSI. I mean, it's absurd. I overdo it on all these because I never have used these more than 15 bar because of the forces generated. But the reality is they're set to seal with a certain amount of force on stretch, elongation on this metal rod when you tighten nuts at both ends. The problem is, like I said, you never get them accurately tensioned because one tightens more than the other, and you'll end up with a full thread on one and only a few threads on the other. It's a pain in the ass. So what I do is I always take one end off, which is the rod end, so that I can pull the rod cap, the bushing, the piston out of the cylinder that way, and I can look at the bore to make sure it's not scraped or scratched. I can look at the seals from the inside. I can look at the urethane bumpers. I can check everything out. And that way, by measuring the distance of thread stick out every time, I can torque them by locking the rod and getting the stretch I need, and they will go back exactly as they were set from the factory every time, okay? And it just saves me the additional problem of trying to reset and hope they seal and getting them wrong. And another little tip, guys, you always go diagonal. I've taken this top one off here. I will do the bottom one here. I will go top here. I will go bottom one here. You never go side to side, one side or the other, because it will cock the plate and you won't end up with correct sealing. You go opposites, just like torquing cylinder heads on race equipment, etc., on cars. So this is a standard. These are 4-inch, 100 millimeter bore cylinders. These are standard. They're the same cylinders, only these are very short ones that I use for the rams, for the ratchets, everything, because these pieces are off the shelf. I can buy all the seal kits, all of the bushing kits. I can replace any of these parts at a moment's notice. And it helps to standardize. It's one of the things that is a problem with a lot of guys' equipment is they may have 3 ratchets, but every one operates differently. They may have this, it just doesn't make any sense. I number everything. I keep it all so it's the same. Interchangeability, this is something we learned from 20 years plus of racing fuel. If it's a custom part, you better build 10 of them. If it's an off-the-shelf part, you can order them and have extras. And when it breaks, and machinery always breaks, don't let anybody who builds you shit tell you that shit doesn't break. Machines are machines, you know, and inevitably it's human error that causes the breakage. They don't usually just give up, take a shit by themselves, but there are things that cause problems. So you have to have or be prepared to, you know, like in racing, blow it up, fix it, and go back and do it again. So this way, by standardizing, I have all the seals for a ram, for any size, anything I do. They're all the same. They all have the same math. They all have the same force. They just have different volumes. The length of the cylinder is your volume. So I'd use a different accumulator for this as opposed to a 4-foot ram, 125 mil, 125 centimeter, 1200 mil. I would use a different, again, volume if I go to an 8-foot ram, a 2.5 meter ram, okay? Because volume in the period of time is how you fill this cylinder in a hurry. And I've heard a million stories. People are like, why doesn't this work well? It's because they've taken a trigger box and accumulator setup for something like this and tried to use it on a 4-foot or an 8-foot cylinder. Kind of silly, but that just shows you a lack of knowledge of how things work, okay? So these inherent industrial technologies have their own world, okay? And to use them correctly, you got to learn about them. This is like anything else, you know? So just I thought I'd give you a quick look as I'm taking these apart, cleaning them up. I'm going to solvent tank everything and have a quick look. It's been a couple of years. And, you know, that way you know what they look like and how they work, okay? So take care. Hey guys, since we're already into it, I might as well continue with the air cylinder wrap. This is your air cylinder taken apart. I can pull the piston out of the bore, but what you have is end caps. And this one, because we're working reverse of the air rams we pull with, we're actually putting air in on the face. So our back end cap is here with our feed. And because these are so small and I feed with such a large amount, I don't double feed these. It's such a small volume. It goes in so quickly. I only have one input. On my others, I have multiple inputs. You also have an air cushion, so when it comes back down, you can adjust your air cushion. There's a little valve that blows through this hole, and you can adjust it with a screw from the outside so that it allows more or less air as it comes back down to give it an air cushion, meaning as it goes rapidly towards the other side, not only will it exhaust, but the cushion is there if it goes too much so it doesn't slam. You have your aluminum or stainless steel cylinder tube, and I use these instead of carbon because carbon you still have to line with metal, aluminum or steel, and otherwise they scrape and they leak. And then you have your piston, which I don't know if I want to actually force the piston out today or not. Piece of wood to pull it here because it's not really aligned in the bore right now. And you'll see your rubber piston is here. And then you'll have a rubber piston seal, then you'll have a hard piece of aluminum, then another rubber piston seal. And this rod is screwed through both, okay? And you always check inside your bores to make sure there's no marring or any dirt or any finish. And these are oiled, you'll notice I oil them so you can see the amount of oil that's in there. And I keep them clean and I will wipe them and then re-oil them when I assemble them. And we've had a whole discussion on that prior, so I'm not going to get involved. This is aluminum. And the difference between this and carbon fiber is pretty minimal. So for the extra kilo of weight or 2, I use these. They're easy to replace anywhere in the world. So that's your rod. You look for scars and scratches. You look for any wear on your seals, and the seal kits come as replacements. Okay. You'll notice there's a pool of oil here from the cylinder because when I store them, I make sure there's oil in them. And here's your rear cap. These are your tie rods. Okay, and it goes in this groove and seals. You know, it's just a pressure fit by stretching these. Okay, so everything has to be clean and perfect when you reassemble it. And I'd mentioned the cushion valve. It's here. I don't use any of these on my rams. I have a different system on the big long rams because this extra never gets really used. On that side, they get used in the pull so much, and it's such a violent, quick action. I don't need an air cushion. I don't want air to build up. I want it to exhaust as quickly as possible. And I limit the stroke so it never slams home. Anyway, and then here's our face side with a replaceable bushing and seal combo. You can see the seals, the Teflon seals, and you'll notice that it's multiply fed here. Boom, boom. But in this, because we're using it in reverse, this is actually the exhaust side. So I'm putting in one set of air and I have double the amount of exhaust on the other end, because I can't put air in under high pressure and quickly unless I can get air out of this cylinder. And again, this one, because it's an air ram and it works a little different than the ratchets, I've allowed the air cushions to exist so they don't slam all the way, because there's no limiting on these. I don't have a leash on them. I don't have a limiter device. So they slam to their full extent of stroke. I actually do limit them, which I won't get into, but I have rubber cushions that go on the rod, because this is a 12-inch stroke, 300 millimeter stroke, and I only use 220 millimeter of it, full stroke. I could have gotten smaller ones, but you know, it's not sometimes you aren't perfect with the geometry when you're building. And on these, I could have gotten, like I said, 120 shorter, 100 millimeters shorter. But instead I had these happen to be handy, and I keep them in stock lengths. So what I did was I just used these, and I limit them by limiting the amount of rod, by putting a bumper stop on it, so that it can't extend any farther. So that's basically a tie rod cylinder, of which everybody uses in rams. And if it's not tie rod, it's a sealed end. It's not usually rebuildable. But anyway, that gives you an idea. When you put these back together, you reassemble everything. If you pull the seals out, you need a piston ring compression tool to get them back in the bore, and you will fight to do that unless you have the right tools. You put them all together, you make sure everything's clean, you seal it all back up, and then you put your nuts on in a diagonal form, snug them, and then torque them in a diagonal pattern to the same lengths that we measured and the torque specs. That way everything goes back exact. Everything's clean and perfect when you reassemble it. And that's how you go through your equipment, folks. This is just a basic cylinder in an adjunct to the air rams, because I was doing this. So, you know, that way you can see how things go apart and back together again. All right? So there you are. And the other issue is, of course, with all of my rams are through ports. I have through ports on everything. I don't throttle ports. If you notice, most airports are threaded, whatever your fitting is, and then there's a very small pilot hole. These are not that. They are full bored through, as big as they can possibly be for the billet end cap. The only other way would be to make custom end caps that are even bigger, so that I could get a bigger hole in here and exhaust more. But again, if you're going to do that, you better make a dozen of them or 20 of them so you have them. And these are orderable. I have them designed. I designed them, so I have them made for me by an industrial manufacturer that makes custom cylinders in the United States. And I use them because they're my design for the way we do things. Anyway, there you go. There is a air cylinder, clevis, billet end blocks, and then the seals and pistons are here. I'm not going to pull it out because I don't need to. And I don't need the aggravation today of fighting getting the piston seals back in. All right? And excuse my hands reaching because my batteries on my fucking remote died because I've used it too much. So we're back to the simple, crude, but effective, big, fat, greasy hand pushing the button. All right? Take care. Well, because I'm busy doing this today, I figured I might as well just do it all. Here's what a piston looks like with a wear ring on it. It's the middle wear ring. These are very conventional pistons, by the way. These are not like what's in the rams I use. These, because of their short stroke, I can get away with a much more conventional, because we're pushing on the face, not on the rod side. The piston can be very short in length. If you notice, this piston for the stroke is only a 50 millimeter piston length. Okay, in the rams I have, they're 300 millimeter long. Because we use them where the rod can wiggle in the bore, the more stability you have here. It's one of the secrets. That's one of the reasons I build them. The middle ring is a wear ring, and these are double seals on both sides. So this is a hard Teflon, and you can replace any and all of these seals. This piece is actually threaded on, and the factory dimples it once they've threaded it to deform the threads so it can't come off. So if you're gonna take these pistons off, you have to work through that, and it's a pain in the ass. But there is a piston. And then here's your cylinder, just a piece of machined, mirror polished aluminum on the end. You can see it. It's all shiny, nice and shiny. And that's what you look for, is you look for, in the orientation it's operating, top and bottom is the piston cocking. Are there grooves worn longitudinally in the bore? It's just like looking at an engine, guys. You got to decide if it's scratched, if it's what. And you can make do sometimes by turning it 90 and then running new grooves. If you have shitty cylinders like some people do that have no liners in them and they wear grooves in them and they leak like a motherfucker, you can get away with it for a short period of time. But again, it's a stopgap for shitty machine design. So anyway, there's a piston cylinder. Here's a piston rod. These are 1 inch, 25.4 millimeter steel, hardened steel, chromed. And these are your pistons, which are aluminum layers with rings that compress into the cylinder. And it came out actually while I was working, and then I'm fucked. So I got to get the ring compressor tool and compress that and put it back in the cylinder, because it's only lightly chamfered, so it doesn't fold in very easily. But I thought, since it's all apart, I'd show you what it actually looks like when you're doing these. So you'll understand that that's what a cylinder looks like over here, all apart. Cylinder tube, rod, piston, end caps, okay? And these are tie rod cylinders. Pretty simple shit, okay? Just you have to make sure you're clean, you get them put together correctly, you don't allow the seals to kink or cock in the bores. So you use a piston ring tool that compresses all of this and then feed it into the bore, oiled and clean. All right, so that's pretty simple. Again, the greasy hand of death coming up to turn the button off. So here we're at the whiteboard. It's just easier to see rather than me and my little finger hand diagrams. What I've got here is a vertical line, a horizontal line, a cylinder, and this distance is the eyes of the mounting, the center point. So depending on diameter, that's how tall, and your middle point will be whatever half the diameter of this is. This vertical, this is your big pivot. So this is a bearing, a shaft, a bushing, this is whatever it is. I mean, it's just whatever it is. I'm not gonna get into machine design on that aspect. Okay, the theory of pneumatic design in the handbook on how all this is done, you got 90 degrees of travel, and that's based on, of course, always you have to set your stroke for this distance. First math you have to calculate. Second math is how high up can you push so that you are pushing, when this is here, how much force is being pushed here and going at the pivot versus moving this device. Now at 45 degrees and it's here, you're going to be putting all your force into it till it finishes at 135 degrees. It's 90 degrees of travel. So 45, 135. There's your distance. Now you can arrange this because of the height factor based on your cylinder. You can arrange this line any way you want by moving the angle of the cylinder up and tipping this line over. So you could actually come in with a cylinder at this altitude, same pivot height, that's going to push here directly. Okay? Now that will mean this is 100% of the force from here to here. Okay, so there is 0 at the pivot. The lower you bring it, the more when this is at this point going into the pivot. Okay, unless of course to solve this flat, you would have to have it at a 45-degree angle like this with your pivot here at half the distance of your cylinder. Let's say this is a 100-millimeter cylinder, so because it's a larger end cap, you can only get 70 millimeter off the ground. So there's your midpoint and you're pushing in this direction. Look at this vector. Again, math kids, vector theory. You can only push so much this way. Now some of that force is going here and some is going there. Until you reach a point out here where all of the force is going into this lever arm. So what's going to happen is you're going to need more force here than you need here to make this move. Hence the bad point where you get fucked by the machine here. So if you start out with the correct geometry so that every 100% of your force is pushing this lever arm correctly, you never have this problem in here between the zero incidence pushing something at this and the perfect point where it's pushing all at the lever arm. This mechanically explains why this works this way. So the trick is, when you design your machine, is to make, however you want to arrange it, you pick a height or you pick a cylinder, you pick one dimension and start working backwards from there and work through the math. And you will come down for the 100 millimeter cylinder, 300 tops, a 250 pivot point, which is here. So at the beginning it's here, it will move through the arc and be here at the end, and you will have 100% through the range of motion. And like I said, you can orient this, the front of my machine is oriented there, and then this is tipped up to here, so the two meet to be at the perfect geometry for this motion. This is all in pneumatic theory, and this is all in machine design theory, and it's all available in books. Now, this makes for a very nice, easy to ride machine. It's based on the cylinder diameter, and this way you can use the lowest pressures, you can make it the safest and easiest to use, and have the most fun with it. And it becomes a very useful machine. But that's the basic theory behind them, is it's just a rod pushing a lever arm. And you can calculate the weight of your machine, and then if your lever, say you're out here, your person is standing out here, okay? So the lever arm is this long on the base of the machine, and you need to orient this lever correctly. From this point to this point, you can calculate the weight of this and the force required here for pressures to move this lever arm, okay? So then you know how to size your cylinders, because you know the distance, it's lever theory, it's mechanics. You calculate 100 kilos here, you calculate your distance, and you know what it takes to move this at perfect geometry. Anything less, and you're going to be just jacking the air pressure up. Okay? So all those various design elements go into making the correct piece of machine. And, you know, most people obviate this. They just get a set of cylinders and they build a frame and they stick it together, and nobody calculates this. This is how you do it to start with, so when you actually put it in metal, you're not getting your ass kicked by the machine and wondering why it takes 1,000 PSI to move you the first 4 inches, and then you fucking feel like you've been hit by a truck after that. How about we just make it so that this lever arm starts here, and it's built, as you'll notice, mine is built this way, like that. And here's the pivot. The cylinders are oriented like this, mounted and mounted. This is 250, this is 300. So from this point to this point, it's perfect geometry. And this lever arm will travel from here up to 46 degrees, 0 to 46. Okay, that's how we did it. So it's how you orient this piece. It's basically a pivot, a lever arm, and you choose your pick point, and something is attached to this lever arm. Now, obviously, this isn't going to be very strong, so you need to do something here. But it's this to this, and it pushes across this distance. Okay? So you orient it from here to here. And then you have to design everything to handle the weight and the forces based on the length of the lever and what you're trying to achieve. Pretty simple, pretty straightforward. Yeah, it's just one of the reasons why this piece of equipment is highly overlooked is because nobody bothers to do this. All right? So that's just a quick one on another machine that's in the archives that we have here that we love, and it's very useful if it's done right. All right? So that's it for today's Stunt Rigging Toolbox talk on some arcane and interesting machines for stunt work.